Hush. It's falling now, so I guess I should start. I'm David Wallace. I'm the director of the Newton Institute, and I'm really, really pleased to welcome you all here this afternoon, and thank you very much for coming. We've got a sort of 5-10 minute slot, but I'm going to say something as director of the Newton Institute, and Robert Lees, who is director of the Smith Institute, will also say something about it, because this is really a sort of double act between the two of us. But it's maybe well, since I guess probably very few of you have actually been to the Newton Institute before. So I'll say just a couple of minutes about what the Institute is and what it does, and then hand over to Robert. Before I do that, because I definitely will forget, anyone who would like to book a taxi and hasn't yet done so, if you can contact any person on the reception desk or simply let me know, then we'll make sure that that happens. Whether it's for people who have to leave immediately afterwards or people who are staying on for the dinner this evening, and we'll be leaving from Churchill College, which is about 400 metres from here. We'll just walk up there and we're just going to dinner when the reception. So coming to the Institute, the Institute is a national facility which runs research programs on behalf in the mathematical sciences, very broadly defined, on behalf of the UK community. The building is actually located in the Centre for Mathematical Sciences, so this whole suite of buildings is actually the math centre of the University of Cambridge. It's a fantastic concentration of research strength. That's one of the things which attracts people here. We run, at any one time, we run 2 research programs. They're typically quite long, 1 to 6 months. So the Institute is focused on long-term research issues. And we cover all kinds of things from the purest of pure maths through to applications which can run from quantitative finance through to biology via astrophysics and climate change and whatever, all with a mathematical underpinning. So it's a fantastic place to be, because the quality of people that we get here and the range of interests that they have is just phenomenal. At any one time, about 70% of the people here will be from abroad. We're mainly supported externally by the Research Council, the Engineering Physical Sciences Research Council, which supports maths. They provide about 2/3 of our funding. We have a major grant from them, and about half of our funding is used to directly to support participants, and half to run the Institute so that participants can actually do some work when they come here. So we're into long-term programs and research, and we leave things open. This is an open place, but whenever appropriate, we like to open the place up for business, which has its own characteristics and its own interests. And we're really pleased to be working with the Smith Institute on this. As far as this meeting is concerned, we've tried to construct it so that there are a couple of talks which we hope will be interesting. Then there will be the panel discussion, which will become a bit more informal. And then for those of you that can stay after that quite informal discussion, latch on to anyone that you think will be of interest to you and discuss this with them. One of the nice things about the Institute is we're open. If you ever wanted to come up for anything else, you just need to look on the website, newton.ac.uk or newton.cam.ac.uk, and if there's anything that you fancy coming to, you can just come. It's nice to know that you're coming in case there are 1,000 people that have the same idea and we can't cope with them. But you're free to come. We don't own any intellectual property. This is a place that facilitates exchange, and that's what this afternoon is about. So I hope that you have a really interesting time, an enjoyable and stimulating time. So I don't think, Robert, there's anything more that I need to say. So without more ado, I should hand over to Robert Lees to say a few words about the Smith Institute to help us in this. Robert.
Yes, thank you, David. As you said, my name is Robert Lees, and I'm director of the Smith Institute for Industrial Mathematics and System Engineering. And we're an organisation that works on the interface between business and the science base. And as part of that activity, we manage the Knowledge Transfer Network for Industrial Mathematics, which is an initiative itself of the Technology Strategy Board, which many of you may have heard of. And this is a new governmental organisation in many ways akin to the UK Research Councils, but its focus is very much on supporting innovation in the business community. The knowledge transfer networks are a way in which the interactions that are needed to bring that about can be facilitated. In our particular case, we're concerned with interactions that involve the exchange of mathematical ideas, bringing people from the business community and the science base into contact with each other in ways that enable them to create new and fruitful interactions. Now, we've known David and his colleagues here at the Newton Institute for a long time. It seemed to us that it'd be very useful to try to build some joint activities around the core Newton research programs. So after all, they represent really unique opportunities where you have an international community of researchers gathering here in the UK for an extended period of time. It seemed a very natural opportunity to try to bring people from the business world into contact in a way that enabled them to interact and discover where the areas of common interest would lie. So we've designed what we hope is quite an intimate meeting in some ways, small, keeping it small, allowing people time to interact. We wanted to explore quite a wide range of potential applications, so we deliberately tried to bring people in from several business sectors, and I think you'll see that reflected in the attendance list here today. What I'd like you to get out of today really are three things. I think first of all, I'd like you to learn something, so be informed from the talks and certainly from the panel discussion as well. I'd like to have an opportunity to network with other people who've come along today, and I hope we've designed a programme that allows you to do that. And also, I'd like you to contribute in the discussion time as well. We'd like to hear your views about the topics that we're going to discuss. And if out of the day you see opportunities that you'd like to follow up, we'd be very pleased to hear from you, and we can look to facilitate further interactions that are perhaps tailored towards your specific needs. We've got some literature on the out in the foyer there about the knowledge transfer network and some of the ways in which it works. We also have an extensive website at industrialmaths.net where you'll find a lot more information as well. So please, if you want to come up and ask me anything about the KTN afterwards, please do. My colleague Heather Tewksbury in the audience there also there to help you.
Great. So, Robert, thank you very much. So, let's make a start almost up to time now. The first speaker is David Hand from Imperial College. David is president of the Royal Statistical Society. I know he is already known to many of you through collaborations which draw on his own expertise. And we're very lucky to have him as a speaker. So, David, over to you.
Thank you very much indeed.
I should say as well, before David starts, is that all of this is being recorded. We record on video all these seminars, so this will be for posterity. The microphone array will pick up any questions, etc., and you'll be able to look at it afterwards. So,
where I trip over, so you've got some outtakes for posterity. So thank you very much indeed for inviting me to speak at this meeting. As you can see, I'm an academic, but I think I'm a rather unusual academic because a lot of my work is collaborative with various sectors of industry. As you will see, I do a lot of work with the retail financial services sector, but I also work with pharmaceuticals and with other sectors of industry. I was asked to talk about frontiers in applications of data mining because I'm especially interested in very large data sets and trying to extract meaning from that. But given the audience I'm talking to, and given the short amount of time that I've got to talk, sort of half an hour including questions, quite clearly I couldn't go into technical detail on anything. That means that this talk is incredibly superficial, and I hope you'll forgive me for that. Perhaps I should also just say, before I sort of dig into the talk itself, that data mining, statistics, and machine learning, which we're going to hear about after this talk, all overlap to a large extent. They certainly have a significant intersection. So some of the things I say may well be repeated or overlap with things Chris is going to say afterwards. So let me begin by saying there are no frontiers in applications of data mining, and that was my initial reaction when I was asked to talk about this. And I thought, well, that's it. This will be a very short talk. Has anybody got any questions? So there are no frontiers in applications of data mining if by a frontier you mean a boundary or limit beyond which the tools are not applied. If that's what you mean by a frontier, well, there aren't any, because data mining is applied just about everywhere in industry now. And to demonstrate that this is true, I pulled down the results of a survey carried out by the organisation Two Crows, of survey of business uses of data mining, and you can see just some of the sort of sectors which data mining are used in industry. Forecasting advertising revenue, churn in various different sectors, claims processing, credit risk analysis, I do a lot of work on that myself, customer profiling, customer value management in general, and all sorts of other things, warranty analysis, whole just about any area you can think of, somebody somewhere is sort of using data mining techniques to look at that. And there are also, of course, countless scientific applications. And talking about data mining in industry, well, to a large extent, this will overlap with scientific applications. So, for example, the pharmaceutical sector, talking about data mining there, are you talking about science or industry? And I will mention some sort of pretty overtly scientific applications which do nevertheless have industrial application later. So I started by saying there are no frontiers if a frontier is a boundary or limit beyond which the tools are not applied, and this is an illustration that there are no frontiers if you define a frontier like that. But if you define a frontier as the limit of current knowledge, okay, then there are limitations, and there are frontiers, and there is scope for more applications. And the reason that there are frontiers, if you take this as your definition, is that new problems arise all the time, new kinds of situations that you haven't encountered before, for which existing tools, methods, models, whatever, don't work. So you have to develop something new. So in that sense, there are frontiers. And these problems come from the interweaving of two strands. The first ones are developments in computers. Of course, the whole notion of data mining has been driven by the development of computers, as also as the whole notion of machine learning. Before there were machines, computers, you didn't have machine learning. So these things are being driven by developments in computers. And the second is new application areas springing up. And we're going to see examples of that in a moment. So let's focus on these two things. The first is developments in computers. So developments in computers have an impact in various ways. One is vast new data sets. When I learnt statistics, when I did my master's degree in statistics, a large data set had 1,000 data points. Now a large data set will have billions of data points. So things have changed. And of course, it's computers, it's databases, it's the ability to process such things which has enabled that. Developments in computers. And then number two here, creative and imaginative people seeing new possibilities of computer power, new ways you can use the sort of raw crunching power to do new kinds of things. Another example, of course, is the web, something completely radical, innovatory, which couldn't have been envisaged before the computer. And there are doubtless other things. These are just examples of new developments which the computer has enabled. And then the second thing I said was new application areas springing up. And I've just put some examples here, but you will be able to think of others yourself. Biometrics, of course, face recognition, this kind of stuff. New application areas requiring new solutions. All of the bioinformatic type realm, of course. New application area requiring new solutions. Detecting terrorists, text mining, and so on. New application areas requiring new solutions. Old areas too, things which existed before the computer came along, are also being changed unrecognisably by developments in computers. So astronomy, for example, used to be done by looking at photographic plates. Now it's done by recording images with charge coupled devices and so on, completely different, these vast astronomical databases which exist now. Particle physics, generating terabytes of data. Well, they did particle physics before we had advanced computers, but the nature of the animal, nature of the beast has changed. And all of these other things, post-marketing surveillance, epidemiology, customer value management, fraud detection, changed radically. They existed before computers, but they've changed radically now because the computer and the dots, again, the ellipsis, many other things which have been changed, many other things which existed before, but which have been changed unrecognisably by the computer. So if I'm talking about frontiers, I want to look at where are the current gaps in our knowledge, what are the important directions for future research, or I've sort of put it another way, data mining comes of age, and I want to show you how data mining has in fact changed over the last 15 years. Very interesting from my point of view because I came up with definitions of what data mining was 15 years ago, and I think they're a bit out of date now, and I will illustrate that. So let's take a step back to the early days of data mining, when the phrase first started being used. In those days, in the very earliest days, and there are papers which use the phrase in the sort of early 80s, and there was a sort of classic statistical perspective in those days. Statisticians would look at what was coming out of computer science community, and look at it regarded in a disparaging sort of way. The initial perspective on data mining was that you take a given data set and you fit many hundreds of thousands, millions, whatever, different models to it, looking for interesting structures and relationships in the data. And it was called, people used the phrase words trawling, fishing, snooping, disparaging sort of words. The point is that if you've got a relatively small data set perhaps, and you try 100,000 different models, you're bound to find something, in inverted commas, interesting in the data. You're bound to find apparent structure if you look hard enough. The key question, and one I'm going to come back to again and again because it's interesting in the context of how data mining's developed, is will it generalize? Typically, you're not interested in the data you've got. Sometimes you are, but I think most often you're not. You want to know whether anything you find also applies to other data sets. But because of this business that you're bound to find something if you look hard enough, statisticians tended to be disparaging about data mining. That, if you like, was the statistical perspective sort of 20 years ago. The computer science perspective, however, was rather different. Some computer scientists are experts in databases. They're experts in storing data sets. And so they focused their attention, their sort of notion of data mining was focused on the particular databases. It might be a database of employees in a company or something like that, and analysing that database and trying to understand what that database looked like. So association analysis is a classic example of that kind of thing. And their perspective wasn't concerned with generalization or inference to a population that the data you had might have come from. It was concerned with describing that data. So any generalization that you carried out wasn't a sort of statistical generalization. It was a sort of implicit generalization. We found this, so we think this is always true. And basically, in the computer science community 20 years ago, they didn't really recognize the statistical issues, the statistical inference issues. And I can recall very interesting debates at conferences and workshops and so on between statisticians and the computer science, people from the computer science community about this. And it was clear that computer science didn't understand the role of inference in this. I mean, perfectly understandable, because when you've got large data sets, the basic inferential risks can often be hidden. You know, I mean, if you've got a large enough data set, things are going to be significant, if you like, so you don't have to worry about those sorts of things. But that in some sense hides the issues. So I want to move on. That's the past, and now let's sort of move on to the present and where things are going in the future. An initial slide here, before I get into examples of where I think things are going into the future, because in this sort of context that we're talking about today, the phrase other phrases are often used to mean essentially the same thing as data mining. Business intelligence is one which is often used. I'm often asked to talk about business intelligence, and they've asked me presumably because they've seen the stuff I've done on what I call data mining. But analytics is another word which is often used in this context, meaning essentially the same sort of thing. And in particular contexts, of course, customer value management will mean the same sort of thing. And examples of the sorts of things which come out of business intelligence and so on are these kinds of things where you can gain a march on the competition, pricing hotel rooms, where you might try to predict the highest prices people will pay without reducing the number of bookings you get, for example. We all know that some airlines do this very cleverly. They do the same sort of thing, and in fact there are organisations which try to predict what airline prices will be over time, so that you can decide when is the optimum time for you to buy an airline ticket. And a similar sort of thing is predicting the likely outcome of blind auctions and so on.
David, can I butt in with a question?
Yeah, sure, please.
Where does ethics come into that?
Aha! Ethics doesn't come into any of my slides, but it's an important issue, yeah. So we'll have to talk about that afterwards, I think. But I mean, I think, yeah, there are all sorts of, I think one of my later slides has a single word privacy on it, and there are all sorts of issues involved with data mining in certain contexts. You're obviously aware of the sort of terrorism stuff and the controversy in the States about collecting huge amounts of data on monitoring individuals, and there are sort of all sorts of ethical privacy sort of issues which are potentially very complicated. But I'm going to come back to those sorts of issues a little bit, but I don't actually talk about ethics per se. So what I want to talk about briefly are some major directions for the future. And the way I think things will go. Now, these are not things which haven't been explored at all in the past. Clearly, everything has roots. Some people will have been looking at these things. I think these are things which are going to be major forces for the future. The first is experimentation. Classically, data mining has been about observational data. The data will have been collected as a side effect of some other process. The example I know a lot about, as I say, I do a lot of work in the retail financial services sector, and when you make a credit card transaction, the data are initially collected so that you can get your bill at the end of the statement can be sent to you at the end of the month, and you can pay it. But once the data has been collected, you gradually accumulate a huge observational database, which you're going to analyze to do all sorts of other things, discover how people behave and so on. And that's a classic example of data mining, primarily about observational data. But more recently, there's been a move towards experimental data and actually deciding to randomize controlled trials and things like that. I say more recently. Quite clearly, some companies involving large data sets did this a long time ago, and my next slide has an example. But the point is that, again, we're driven by the computer, the power of the computer. It enables products to be customized to each person. And yeah, so here's my first example of a company which used data mining and experimenting a long time ago. But most companies in the retail financial services sector haven't caught up yet. They were doing, Capital One set up some sort of 15 years ago, and was one of the first, one of the founders of Capital One describes it not as part of the banking industry, but as part of the data industry, and they really got to grips with the potential, and it very rapidly became one of the biggest banks in the US. Now it's got over 6,000 different credit card products, but it doesn't, when you apply for something, you don't have to choose one of those 6,000. It doesn't give you a choice of all those 6,000. What it does is carry out a huge number of experiments each year, enable it to work out what is most appropriate for you and what you'll want. And the sorts of things it experiments on, I've just listed some of them here: products, characteristics of products, prices, how they're described, how they're marketed, account management, blah, 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 carrying out lots and lots of experiments a year so that they understand how the customers behave, what the customers want. Perhaps I should say a little bit about ethics. This is not necessarily, you can look at this in two ways. One is so that they can make the maximum profit, but you can also look at it the other way, so that it will give the customers exactly what they want. I mean, there are two ways of looking at these things. And I've got some quotations from some statements by a Capital One employee who illustrates the sort of thing that they did. A couple of slides of this. We test every change in procedure, every job applicant, as well as every product offering, even down to the colour of our monthly statements. So they really do understand what's going on. We record every customer interaction, every card purchase. We collect data patiently from various lists, and then with the patience of a good scientist, because that's really what they are here, run experiment after experiment. For every action we've taken, we know what the reaction's been. If we sent you a blue envelope or a pink one, we know which one you received and how you reacted, and so on. And then I've got a specific example, which is their phone bill. We pay for incoming customer calls, which is a good start, but the calls were taking too long, and our analysis demonstrated the problem was firmly with the way they did it rather than the customers. And a problem which you'll probably be familiar with, calls were constantly being transferred all the time, and we've all experienced this sort of thing, damned irritating, frustrating customers. They looked at various obvious solutions, more training, customer selected menus, didn't work. And then they came up with clearly a model built from data mining, predict the call reason and send the call to the person that you think is the most likely person they actually want to talk to. So a nice example of data mining. Capital One is an unusual company because it was doing this sort of thing way back. It's very clearly ahead of the market, but others are sort of catching up now, and I think this is a wave of the future, experimentation. And another little example of experimentation, relatively recent, Google has a thing called AdWords, which allows you to run experiments on the web to see which advertisements are most effective. Now, there are all sorts of problems with experimentation and with observational data, and this is where statistical ideas, I think, are going to become more and more important. I've already referred to data miners being a bit slow to understand that it was really inference that you're interested in. And clearly here, what I am talking about is inference. You don't care about the data you've got. You're trying to make some statement about a future population of people. And the randomized controlled trial, in some sense, is sort of gold standard for that. But even then, there are all sorts of issues you have to be aware of so that you don't make mistakes. For example, I've seen examples where people use different server fleets for control and treatment arms of the experiment, and then you don't know if it's because they're using older servers for the treatment or whatever. And there are various other kinds of mistakes which have been made. A sort of parenthetical comment here. The Red Queen effect. This is how you've got to keep doing things in order to stay where you are. I've heard people say that no experimental innovation in the context of customer value management stays ahead of the competition for long, so why waste time doing it? It's true that it doesn't stay ahead of the competition for long because there's generally a lot of mobility in the sorts of, at least in every sector except academia, I think. So, you know, if you do make an innovation, it's not going to be long, a few months, a year perhaps, whatever, before your competition also becomes aware of this innovation and if it's good, starts to use it. But the point is that all of these sorts of innovations are incremental. If you are not aware of these things, if you don't do these things as well, before long you'll find yourself not just a little step behind, but 10, 100 little steps behind. You can see where that leads you as you go out of business. So experimentation was my first big sort of thing for the future. The second one is anomaly detection. This is a particular area I'm especially interested in, so I couldn't resist putting it up there. And I'm going to give you some examples. One example of anomaly detection is fraud detection. I have a little group working on this, and fraud detection applies in various areas. In fraud detection, you're looking for anomalous behavior, essentially. And it can be in the banking sector, telecoms, whatever. It can also be in other areas, for example, scientific research. Another little example of anomaly detection, one of my PhD students, James Bentham. We're working with the National Patient Safety Agency trying to identify common incidents which happen to patients. Maybe it's difficult to unscrew, or maybe the packaging for a particular medication isn't ideal and people keep taking overdoses with that medication. Not huge numbers, but enough that you want to do something about it, and various other things. And these are just three little examples of the sort of descriptions of incidents we get. This immediately shows you that this problem is tough. It involves text processing. And what we're trying to do is to map each of these descriptions to a point in space and then observing that there's a little cluster of similar, in some sense, incidences, which we can then, the National Patient Safety Agency can go and investigate. A similar sort of thing, anomaly detection again. I'm working with a guy, ironically enough, from China, we're working on detecting clusters of earthquakes. Anomaly detection again, because there's a background sort of occurrence of these things. Another one, another PhD student of mine, I couldn't resist this. It's nothing to do with industry, but they're beautiful pictures, so I couldn't resist. We're trying to detect anomalous, unusual astronomical objects in these vast databases that I referred to at the beginning. You couldn't do this sort of thing before the computer, and various other areas that I've worked on or working on where we're looking for anomaly detection. So I think anomaly detection is a big thing for the future. Again, people have worked on different kind of anomaly detection in the past, outliers, whatever. But I think this is now becoming a sort of field in its own right. All of these things are different application areas, but they have a lot in common. A third area is display and visualization. Again, of course, people have worked on these things, but again, I think the sort of momentum we have, the computer is carrying us forward to sort of really exciting things in the future, and I think this is going to be a big area. Virtual reality, perhaps. I know some people here are working on this sort of thing, virtual reality for exploring large databases, and I do wonder if it's going to be, in some sense, the next big thing after I don't know how to pronounce this. Okay, thank you. And then I think finally I'm going to come back to this notion of getting to grips with inference. As I've said a couple of times now, data miners have been slow about this. I'm making gross generalizations here, of course, but I think that's true. And they often risk things, aren't aware of the problems, such as selectivity bias and so on. Remember my little examples of server fleets. Oh, not the last one, the fifth one, the last one is merging data sources. This is clearly, again, people have been doing this, but it's increasing momentum, happening more and more, where different sources of data are coming together. Now, I know some people here work on data fusion in a certain way, information fusion. This is an example of the sort of thing, merging of data from official sources with corporate sources and from individuals. I've got to leave a few minutes for questions, haven't I? So, okay.
5 minutes, that would be great.
Okay.
Finish in a couple of minutes.
Okay, thanks. So there are different kinds of data, and again, statisticians have tended to use numerical data, but all of these sorts of data are becoming more and more important. And again, I'm not saying that these haven't been explored before. A lot of them have been explored in considerable depth, but they are becoming more important. Streaming data in particular, I think. Here's this slide. Two things that I haven't mentioned in detail are data quality, which is, of course, absolutely central if you're going to draw any valid conclusions. And I can give a whole lecture course on that if you like. And the other one is privacy, and the notion of privacy in the sort of web world, which is changing the meaning of the word, I think. I want just to conclude with a couple of slides describing credit scoring, this area that I do a lot of work in, just to illustrate why it's a high-dimensional problem. So, whenever you carry out a credit card transaction, between 70 and 80 items of information are recorded on you. They're the obvious things like amount, nature of the purchase, the time, the point of sale type, and all sorts of things. But about 76, in fact, in one of the banks we work with, items of information are recorded. So that's pretty high-dimensional. But of course, you don't just make one transaction. You make a lot. You might make 2 a week, so 100 a year. So you might have 7,000 to 8,000 dimensions per year describing an individual credit card, in fact. What the banks have to do then is summarize these several thousand down to descriptive characteristics of the use of that particular credit line. So there's one high-dimensional problem, trying to reduce it down to something manageable. But of course, people have multiple credit lines. They probably have multiple credit cards. They've got a mortgage, they've got car finance, all these other things. So again, now we've blown up the dimension again because of the multiple credit lines. So what we have to do then is summarize. We're interested in describing a particular customer, for example, deciding how risky they are, if we're going to offer them another loan or whatever. So we have to aggregate these things and pull them down. And just to give you an example of the sort of problem, Experian ScoreAx does this, produces for individuals about 400 variables, which they call standard aggregated attributes describing an individual. So again, pretty high dimensional problem. And of course, this whole thing is not static. Regulations change, new information becomes available, and so on. And what we're interested in doing is building credit risk models using these. So a high-dimensional problem, through several stages. And there are all sorts of other changes going on. The economy changes, competition changes, the technology changes, which is what this is all about, really. And there I'm going to stop. Thank you.
Great. Well, that's very good, and thank you very much indeed, David. So we have 3 or 4 minutes. I mean, we'll obviously open things up in the discussion session, but might well be some specific questions people want to follow up on now. Yes, please.
David, I'd like to ask you if you can say something about the value of information. So just to return to your web example, a lot of people collect information using cookies or display advertisements on web pages, but most sophisticated users now will just have a plugin for their browser that erases their cookies after the session or blocks advertisements. Soon all internet users will be doing this, and you'll have to incentivize the user to allow your cookies or allow your ads. So how much should I pay a user to let me drop a cookie past the session or let me show them an ad?
I think that's an interesting question because of I can't answer the question, threepence. I don't know. But I think it's an interesting question because of the premise. You said all internet users will be doing this as a matter of course. I would have said that most internet users don't care. And aren't
If there were
or
a button on your
sophisticated.
television to just block advertisements, how long would it take you to turn it on?
But advertisements aren't they working in the other direction? I mean, information recording your sort of how you surf the internet and so on. I think that's different. I agree with you. It wouldn't take me very long if I could block advertisements. But we all record and fast forward now anyway. So but I think the fundamental notion of privacy nowadays, you've only got to look at the social networking websites. I mean, I suspect people in this room, I see a lot of grey heads, you see, are very different from what's happening with youngsters. And you're on the cusp, obviously. I think people aren't as concerned about this as we fear they might be, in fact.
Yes. Hi.
I know, as you've said, that anomaly detection is close to your heart. Do you think people will still concentrate on positive anomalies rather than negative ones? The example I give is that they're more interested in finding the fingers in the data than the fingerprint in the data.
Yeah.
Yes? The fact that, you see what I'm getting at, that people are too keen to see the positive evidence rather than the lack of positive evidence.
Yeah.
And the reason why I'm concerned about this is it's very hard to refute, if you like, the lack of positive evidence. And you've only got to look at terrorist accusations where people are accused of thinking about doing something. Now, you might be able to extract from a database that you might have been thinking about something. Are you equally concerned about this difference between fingers and fingerprints?
That's very interesting. I mean, in some of the sort of anomaly detection tools we've developed, so a classic example is looking for a little peak of probability density, so a little cluster, like my National Patient Safety Agency stuff, a little cluster of events or incidents or whatever. And people have said, yeah, you can turn this round and look at where there's a little sparse region of these things. I suspect that the former will be usually the things that people are interested in. But like you, people have given me examples where it is the other way around. But I guess I've been focusing on the former. So.
Well, if we could thank you very much again, David. Let's break from that. We can come back if you have other questions. They can be picked up in the session.